P.6 Types of Variation. In this section, we will write direct variation equations and also use inverse and joint variation models. Now, the key to being successful with these variation problems or these types of variation problems is knowing and being able to recall what the general equation for each type of variation looks like or what it is. This will be how you'll start every problem that you'll have to do. So to start us off, direct variation always has this general form for its equation, y equals k times x. And that equation would be read, y varies directly with x, or if you're given the wording y varies directly with x, you would be able to write that equation, y equals k times x. Now, as you can see in the direct variation equation, and it will also be in the other two equations for the other two types of variation, we have this constant of variation k. K is always the constant of variation for us with these different types of variation, and k always has to be a non-zero number in order for us to be able to work with these different types of variation. Our second type of variation is called joint variation. This looks a lot like direct variation, except it is multiplying multiple pieces of information with the constant of variation, whereas direct variation is just multiplying one variable along with that constant of variation. And then finally, our third type of variation is called inverse variation. This has the general equation of y equals k divided by x. So again, please take some time, commit these three different general equations to memory. These are really going to be your key to being successful with this material. So the first type of task you'll have to be able to complete is to tell whether a given equation shows direct variation, inverse variation, or neither type. In order to do this, how you need to approach it is that you're going to take the equation that you're given, solve it for y, and then determine if the equation is in the form for either type. Is it in the form for direct variation? Is it in the form for inverse variation? And if it's in neither one of those, then neither would be your answer. So if I look at example A, and I want to solve this for y, since I see x times y, to undo multiplication, I need to divide. And if I'm solving for y, I need to divide by the other variable, which is x in this case. So this equation, when solved for y, is 7 over x. So now we are looking at, does that equation look like direct variation? Does it take the form y equals k times x? Does it look like inverse variation, y equals k divided by x? Or does it look like neither of those options? Well, in this case, this would be an example of inverse variation where 7 will just have taken place of that constant of variation k. For example B, we again have x times y, this time equals 1/3. So again, in order to solve for y, we're going to divide by x. But now, in order to simplify this a bit more, we need to recall that dividing by a value is really the same thing as multiplying by its reciprocal. This is going to allow us to work with these fractions a bit better here. So the reciprocal of x is 1 over x. So when I multiply those values together, I end up with this equation, y equals 1 over 3x. That x is in the denominator. Make sure that is very clearly written that way. So now, is this equation, now that it's solved for y, an example of direct variation or inverse variation? This one is inverse variation again because that x variable is in the denominator. That's really our big key. For part C, we don't have any work to do to solve this for y because it already is y equals So we just have to look at this and ask ourselves, does that equation take the form of either the direct variation equation or the inverse variation equation, or is it a neither type of variation problem? This one is neither. We have 7 minus x. There is no subtraction in either the inverse or direct variation equation, so this is neither. For example, D, in order to solve this for y, we'd have to multiply both sides of our equation by 4 to get rid of that denominator or that fraction. That would leave us with y equals 4 times x. And now we have to ask ourselves, is that in the form for direct variation, inverse variation, or is it neither type? This is an example of a direct variation equation. The next type of problem you're going to have to be able to solve would be when you are given a type of variation and some other numerical information, and be able to write the equation and then use that equation to find some other values. The key to these is really determining which type of variation the problem is using, and then working with that specific general equation to complete the problem. So in this case, in number 6, we're told the variables x and y vary directly. This is our key, that we have the term or the words vary directly. So this tells us that we are going to be working with direct variation, which we then need to recall the general equation is y equals k times x. Once we have that general equation, we can use the first information that we're given here. We're told that x equals 3 and that y equals negative 5. And we would plug those two values into our general equation. And then we just have to finish solving for k. We need that constant of variation to be able to write the equation that this particular problem deals with. So in this case, in order to solve for k, since these are being multiplied, we would divide by that negative 3. So then k would equal positive 5/3, since a negative divided by a negative is always a positive. So once you have that k, that constant of variation, you have to write the specific equation for this problem, which means you take that general form, in our case, the general form of direct variation, y equals k times x, and you replace k with the value that you just solved for, and this is the specific equation for this problem. Now what you do, the second piece of this, would be find y when x equals 12. So that tells us to use our equation, substitute in the information that we're given. So we're going to have y equals 5/3 times 12. And we would just finish solving, or in this case, just evaluating for the remaining variable. So if you want to use a calculator, you could do that, or you could simply simplify some values here using a little cross simplification, and then we would just be able to multiply 5 times 4, which is 20. And this is the second piece of the problem that we needed to complete. Our next example, again, the key is to determine which type of variation this problem is using. In this case, we see the words here that we have variables that are varying inversely. So that tells us this is an inverse variation problem. Then once we know it's inverse variation, we need to recall the general equation, which is y equals k divided by x. And then we take the two values for x and y that were given together, 6 and 3 in this case, and we plug those in for each variable where they belong. So 3 equals k divided by 6. And then we finish solving for that k, so we have our constant variation. In order to do that, we would be multiplying each side by 6. So our constant of variation is 18 for this problem. Once you have the constant of variation, it's time to write the specific equation for this problem, which in this case is y equals 18 over x, because again, this is inverse variation. We have to use that form of the equation and replace k with the value that we found. Again, we have a second task in this problem. We are told to find y when x equals 9. So that means we're going to take the equation that we just wrote, the specific equation that is, and substitute 9 for x, and then just simplify and find that y equals 2. One more similar to this, dealing with our third type of variation, joint variation. So we see the words here that these variables vary jointly. So the general form, general equation for joint variation is z equals k times x times y. And we are given the fact that x equals 2, so we're going to have k times 2, that y equals 4, and that z equals 24, so the whole thing is equal to 24. Again, just have to solve for k, just like in the other two previous examples. This time we have to multiply to simplify the right-hand side. Then we can divide to solve for k and find that our constant of variation is 3. Again, after you have the constant of variation, you write the specific joint variation equation for this problem. So that would be z equals 3xy. There's your first task done. Now we have to find z when x equals 4 and y equals 5. So this again is where you use your new specific equation, plug in the values where they belong, and either solve or just simply evaluate, like in this case, multiply those numbers together, and we would find that z is 60. So now you've gone through one of each type of problem with the 3 different types of variation. Notice that the process is still the same. Really, what's the difference in all of them? It's which general equation you started with and then worked with throughout the rest of the problem. The next type of thing you're going to be asked to be able to do is take an expression or a short sentence and rewrite it as an equation using what you know about direct variation, inverse variation, and joint variation. And the nice part about this is when you're writing the equations, you really can just work from left to right in the wording that you're given. So example, for part A, if I'm told that z varies directly with y, okay, there's the first part of that, the first half. Z varies directly tells me z equals, as soon as you see varies either directly, inversely, or jointly, you put your equal sign. And now since it's directly, I know that that is my constant of variation times the variable. So in this case, that variable I'm told is y. So I would have z equals k times y, and that's what I get from just the first half where it says z varies directly with y. Now the second part of it, and inversely we know means we're dividing by the next variable, which we are told is x. So the equation that we would get from that problem would be z equals k times y all divided by x. Part B, again, just work from left to right. X varies jointly, so we know right away x equals, as soon as we see the first word varies, that's where the equal sign goes. Jointly means we have our constant of variation, and then we're multiplying the next however many variables it gives us. So that's t times r in this case. And then inversely with s, so that whole thing would be divided by s for that inverse variation portion of the equation. Lastly, we have to be able to take board problems and do a very similar process that we started out with, reading through the problem, determining which type of variation we're dealing with, using that general form to find information, and before that even being able to write the equations. So again, first thing we always have to do, read through the problem and figure out which type of variation we're dealing with. In this case, we see the terms or the words varies directly. So we know this is going to be a direct variation problem. So we can set up our general form for this using the variables that were given. Since it says time t, it takes diver to ascend safely, safely to the surface, varies directly. So that tells me t equals. So really, if we just cut out some of the extra information, we know t varies directly, so what's underlined in red, width, depth, d. So that, if we kind of eliminate all the rest of the excess, we would have t equals k times d for the general equation using these specific variables from this problem. Once we have that, we can just look for values that would be input together. That would be our next sentence here. It takes a minimum of 0.7 minutes, so that's a time that would go in for t. So we have 0.75 equals k times the depth would be 45 feet. So again, it says our job is to write an equation that relates the depth d and time t. So that means one of the things that we have to do, the first step really, is figure out what that constant of variation is. So solving for k means we'd have to divide both sides by 45. And that would give you approximately 0.017 if you kept it as a decimal, like your calculator would show you. Or better yet, sometimes changing that to a fraction could keep you a little bit more accurate. Realistically, at this point, either way would be acceptable. So let's say just for now, I kept this as the decimal, 0.017, round it to the nearest thousandth like we are supposed to do our automatic rounding rule. So now, just like earlier in this section, once you have your constant of variation, you can write the specific formula, or the equation rather, which in this case is t equals 0.017 times d, and then use that, in this case, to predict the minimum time for safe ascent from a depth of 100 feet. That means we're going to take the equation that we just wrote, and we're going to plug in the 100 feet for the appropriate label d for depth. When we multiply, we have 1.7, and since this is a time, we have to look back up in the problem and find our time unit and make sure we label that answer accordingly. So in this case, we would have 1.7 minutes would be the minimum time for a safe ascent from that 100 feet. Last one, same idea. Read through the problem, figure out which type of variation you are using, be able to write the equation from that using the specific variables in the problem, and then move forward like we've been doing. So in this case, we don't find which type of variation this is until much later in the problem here. It tells us that the intensity varies inversely with the square of the distance from the source. So writing that equation, what we're going to use, intensity will be a capital I variable. And since we have varies inversely, we know that's going to be K over or divided by the square of the distance now. So remember, square means that we have an exponent of 2. So the distance squared is what is in the denominator in this general form based on what we're told. So it's a little different twist on this. This can happen. You're told that something is squared or cubed or whatever the case might be. You can still include that in these different equations. Now we're at the point where we can just go back through our word problem and find information to plug in for each of the variables so that we can find K. So we've got a distance of 1 meter. So we'd have 1 in for that variable D. And the engine noise is 10 watts per square meter. That's the intensity. So that's going in for I. So now if we want to solve for K, 1 squared is just 1. So realistically, we don't have much to do solving. We've got our constant of variation at 10, which means we can write our equation, I equals 10 over D squared. And this is the first part of the task you were given in this problem. No, I'm sorry, it's not. You're not told that you have to write the equation. However, you do need the equation so that you can answer the question, which is what is the sound intensity at 15 meters? Now that you have this equation, even though it's technically not one of your answers, you still need to have it to work with so that you can take that equation and plug in 15 for that distance. Remember, it is being squared. And now we just have to evaluate this. 15 squared is 225. So then if we were to take 10 divided by 225, we will get 0.04 repeating, or 0.044 if you'd like to round it to the nearest thousands. And then intensity, if we look back, the unit or the label for intensity is right up here, watts per square meter. And if we wanted to kind of shorten it instead of writing out all the words, watts is a capital W and square meters would be just like it always has been for us in the past. So this is actually what you need to ultimately find for that problem.